Now what I want to do is look at the heat transfer from the steam perspective. Steam control volume. So with the steam control volume, I have this, it's going in at state 1 and it's leaving at state 2, and we can draw a boundary around it. So there's the boundary that's around it, and what's happening is the steam is losing heat, so heat is leaving, Q dot is leaving as it goes from 1 to 2. So I can apply a first law to this. So now what we have is I drew a sketch. We have an open system for heat exchangers. Pressure is constant ideally, and we have that delta KE, delta PE, and W dot are equal to 0. So all those things. We aren't given information about velocity, nothing's moving up and down, and there's no paddle going in or out of the system. You have to think about that. So now if I apply this, so I have Q dot plus M dot steam times H plus KE plus PE1 is equal to W dot plus M dot steam times H plus KE plus PE2. And I get rid of the kinetic and the potential energies and of the work. And we end up with that Q dot is equal to M dot S times H2 minus H1. And if I substitute in, I have 5 mass flow rate times 160.5 minus 2570, where we have the Q dot is equal to minus 12047.5 kilowatts. So that tells us what the heat leaving is. Now where is it going? It's going into the cooling water. And so now let's look at this from the cooling water perspective. So now I have the cooling water, and we'll have the control volume around the cooling water. And I have it going in at 3 and leaving at 4. And we have the mass flow rate of the cooling water, which we don't know. So we don't know the mass flow rate of the cooling water. So we don't know that. That's one of the things we need to find. But we do know the heat coming in is this. So now it's heat going in, so it's plus 12047.5. So now I do the same first law analysis that we did, or a similar first law analysis that we did before. So I have Q dot plus M dot cooling water times H plus KE plus PE3 is equal to W dot plus M dot cooling water times H plus KE plus PE4. And again, the changes of kinetic and potential energy are 0. The work is 0. We get rid of those terms. And I have that Q dot is equal to the mass of the cooling water, mass flow rate times H4 minus H3. And this is plus 12047.5 is equal to the mass of the mass flow rate of the cooling water times H4 167.3 minus 104, and we get the mass flow rate of the cooling water is equal to 190.3. Kilograms per second. So it's obviously a lot more cooling water is required. The steam gives up a lot of energy per unit mass, and this has to have a lot of mass because it doesn't pick us up as much per unit mass. Now there's one other way that we could look at this heat exchanger, and sometimes one can do that, so I thought that we would show that as well, just so that we see a whole different way not a whole different way, just another way to do the first law analysis. So I have a choice. I could put the control volume around the whole heat exchanger. I could put it around the whole heat exchanger, in which case we would say Q dot is 0 because all the heat flow, all the energy flow occurs within the boundary. There's nothing crossing the system boundary. There's no work being done, so Q dot and W dot are equal to 0. And so now, but I have two things going in and two things going out. So I would have Q dot plus m dot of the cooling water. And I'm going to make life easier for myself and you. Let's say that delta K equals 0 and delta PE equals 0. So I don't have to write as much and you don't have to write as much. So I have m dot of the cooling water times H. This is the in. E in equals E out. H3 plus m dot of the steam times H1 is equal to W dot plus m dot of the cooling water H4 plus m dot of the steam times H2. And the heat and work go away, they're 0. And basically what we have is m dot of the cooling water times H4 minus H3 is equal to m dot of the steam times H1 minus H2. And what this is telling us is that the energy given up by the steam is the energy picked up by the cooling water. And in this case, you know everything except about this except m dot of the cooling water. So you get m dot of the cooling water, you get the same number, 193 kilograms per second. So this is a heat exchanger, and this will finish the example problems for this. What we want to look at now are a couple of examples that are at the end of the chapter, and I just wanted to discuss them with you and go over the high points. So one looks at windmills. And this is example 3.8. So if you want, you can look in the text at 3.8, pause this, and look and see. But in any case, I wanted to show you what was involved. So if I have a windmill, the text has a better drawing. And it's going to have a velocity V1 going in there. And if I look at the windmill, so we basically know that the kinetic energy of the wind is being used to create mechanical energy. And if I turn around, and this is a sideways view, if I look at this, here's the blade. In this, actually I should make this a dot. And so this is the area A. So that's the area that the blade goes through. So when I look at it, the wind is going, it's spinning around and doing that. And what we're going to do is we're going to assume that V2 is equal to 0. So the velocity leaving is 0. This is not the case, and we'll talk about that at the end, as to how to determine that. We're also going to say that the change of potential energy is 0, and that the heat flow is 0. And we have some other things that we're going to talk about, but I'll do that. So now what we have is we did a sketch. So we have the windmill. It's an open system. The process is P equals C. And it's also T equals C. And we'll talk about that. The temperature of the air doesn't change. And obviously there's energy, so we'll do a first law analysis. Q dot plus m dot times H plus KE plus PE in is W dot plus m dot times H plus KE plus PE out. And so what we're looking at is we saw that there's no heat flow, there's no change of potential energy, and the temperature of the air doesn't change as it goes across here. And what you don't know yet is that H is equal to H of T for air. Therefore, delta H is equal to 0. So you don't truly know that yet. And that KE2 is 0 because we said V2 was equal to 0. So I have that. So then I end up with that the work is equal to the mass flow rate times the kinetic energy. So I have this in, and I should point out, because this makes everyone crazy. So the large KE is 1/2 mv squared. If I divide by m, KE over m is equal to v squared over 2. And this is small ke. And so what happens is people want to put the m in there, even though it went away, they want to put it in there. And that's the kinetic energy that's used here. So I have that W dot is equal to m dot times v squared over 2, and m dot is equal to rho v1. And so now what we have is that the power is equal to rho 1 A1 V1 cubed over 2, and A1 is equal to pi over 4 d squared. So I could substitute this in here. Now what is the point of doing this? Why do they make windmills that are big? So if you go out west, you see these huge windmills. Why? Because the power varies as the square the diameter of the area, right? So we have the diameter, so that the diameter is important, and it varies as the cube of the wind velocity. And so the greater the wind velocity, so out west where they have winds of about 20 knots blowing all the time, it's a great place to generate electric power. The only thing that grows there are corn and animals, so the people are few and there's not much industry. So one of the challenges is getting electricity from there to where there are people. So that's another discussion for another time. And so what happens is I see this, and this also explains drag forces. So as cars go, this work, but also drag forces. This relates to drag forces. So drag forces on a car. And why do you need a lot of power in the car to go fast? Because your drag forces on the car varies the cube of the velocity. And so you need more and more horsepower in your engine if you want to go really fast, because the drag forces increase significantly. And in the text it points out that I need to have an exit velocity. So you actually need to have a velocity so the air gets out of the blade. It doesn't just stop. And so with that, the W dot actual is about 0.593 times W dot theoretical. And this was W dot theo. So it's about 60% of that is the best you can do, and then you bring in all your other factors that reduce it more in terms of mechanical efficiencies, etc. And now, one last problem. So let's set this up. This is example 311. And so you may want to look at 311 and see what it says. It's a power plant, and it introduces the concept of efficiency for a power plant. So with a power plant, it runs on a cycle. I have Q dot in, and the heat that goes into a power plant, some is converted into power, work that we want, the rest goes out as heat rejected. And so the efficiency do eta. This is for thermal efficiency of the TH, is equal to desired effect cost of effect. So what we want is to produce power, and what it costs us is that the energy that we put into it. And so we're going to look at that. And conceptually, we can look at the Q dot in and see where it goes. So another way, and this isn't in the book, but if I were to do it again, which isn't going to happen, I would do this. So this represents Q dot in. Where did the heat go? It didn't disappear, it didn't stay in there. So some of it was converted into W dot net. The rest is Q dot out. And so I can think about this, and obviously I want this piece of pie to be as big as possible, and that gives me the thermal efficiency. So the thermal efficiency is relating as to how big this is to the input. And so now let's look at the example itself. So what we're given is that this power plant produces 1,000 megawatts. And we're told that the thermal efficiency was 52%. So now I can use this information to find the heat in, and we're asked to find the size of the tanks that we need for 3 days worth of oil. So we have all this stuff, how much oil you're using, blah, blah, blah. So anyway, let's find that out. And we're also told that the heating value, H sub RP, which is basically the enthalpy of the fuel, is 43,000 kilojoules per kilogram. So I have that. Oh, and I taught all these things that I have to write down that I didn't think about. And we're told that's why you're writing the sketch and putting all the information down, which I did, but I have to copy my notes. 990 kilograms per cubic meter. And so what we want to do is find the size of the tank where L is equal to D, so we hold 3 days worth of fuel for this plant. So what we're doing is first with the thermal efficiency, 0.52 is equal to 1,000 megawatts over Q dot in. So Q dot in is equal to 1923 megawatts. And Q dot in is equal to the mass flow rate of fuel times the heating value of the fuel, or the enthalpy of the fuel. So I have 1923, 3 zeros, kilowatts, and this is kilojoules per second, is equal to m dot f times 43,000. And so now I can get that m dot f is equal to 44.72 kilograms per second. So that's how much we need, and then obviously we have to figure out the seconds per hour, the hours per day, times 3 days, and get the total amount of fuel that we need. And so for 3 days, MF is equal to 1.159 times 10 to the 7th kilogram. It's a lot of kilograms. Oh, it's a lot of kilograms. There's 1,000 kilograms per metric ton, so there are a lot of metric tons involved too. So there's a lot of oil that's involved. And now what I'd like is to have the volume. So I now want us to find the size of the tank. So I have the size of the tank where L equals D. And I want to see how big this has to be for this oil. So the volume of the tank is the mass of the fuel, MF in kilograms, divided by the density in kilograms per cubic meter. So the volume of the fuel is equal to 1.159 times 10 to the 7 divided by 990. So this is going to be 11,708 cubic meters. And so then the volume is pi over 4 d squared L, and that's equal to 11,708. And so if I do this, I get D equals L is equal to 24.6 meters. So that gives us our size perspective. Now, and for homework, 353, 355, 361, 367. What I hope you see with this is that with very simple thermodynamic analysis, I can do some fairly interesting calculations. So if I were an industrial engineer, I might want to figure out how much space should I have for storing fuel? And do I need a week's supply of fuel? And am I assured of that if there's a storm or an interruption, will there be enough storage capacity? If I have that amount of storage capacity, I have to be paying someone money to pay for it. Do I want the supplier to guarantee that he can provide it or she can provide it, and so it's on their barges, rather than, so I don't have to pay them until they deliver it. So all this type of industrial engineering decision making can be done with simple thermodynamics. And so this is part of the power of thermo. Very simply, we can look at some fairly complex systems.